Amplifiers are essential components in electronics. They increase the amplitude of electrical signals. Large signal amplifiers in particular handle signals with significant power levels. These amplifiers find applications in audio systems, power supplies, and RF communication. They are crucial for driving speakers, regulating voltage, and transmitting high-frequency signals. Understanding large signal amplifiers is vital for designing and analyzing various electronic circuits. One key aspect of large signal amplifiers is their efficiency. Efficiency refers to how well an amplifier converts DC power into amplified signal power. Higher efficiency means less power is wasted as heat. This is especially important in high-power applications to prevent overheating and improve overall system performance. Power amplifiers are categorized into different classes based on their operating characteristics. Class A amplifiers are known for their high linearity. Linearity refers to the amplifier's ability to faithfully reproduce the input signal without distortion. Class A amplifiers operate over the entire input signal cycle. This means the transistors are always conducting, leading to high power dissipation and lower efficiency. However, their excellent linearity makes them suitable for high-fidelity audio applications. Class B amplifiers, on the other hand, offer improved efficiency compared to Class A. In Class B operation, each transistor conducts for only half of the input signal cycle. This reduces power dissipation but introduces crossover distortion. Crossover distortion occurs during the transition between the two transistors, creating a noticeable distortion in the output signal. To overcome this, Class B amplifiers are often used in a push-pull configuration. The push-pull arrangement uses two transistors, each handling one half of the input signal, effectively eliminating crossover distortion. Tuned amplifiers are designed to amplify signals within a specific frequency range. They are commonly used in radio receivers and transmitters to select and amplify desired frequencies. The Q factor, or quality factor, of a tuned amplifier determines its selectivity. A higher Q factor indicates a narrower bandwidth and better selectivity. Tuned amplifiers can be single-tuned or double-tuned. Single-tuned amplifiers use one resonant circuit to select the desired frequency. Double-tuned amplifiers, as the name suggests, use two resonant circuits coupled. This coupling allows for a wider bandwidth and flatter frequency response compared to single-tuned amplifiers. Stagger tuning and synchronous tuning are two techniques used in double-tuned amplifiers. Stagger tuning involves slightly detuning the two resonant frequencies to achieve a wider bandwidth. Synchronous tuning, on the other hand, keeps both resonant frequencies the same, resulting in a sharper frequency response. Time-based generators are circuits that generate periodic signals, often used in oscilloscopes and other time domain measurement instruments. A common type of time-based generator is the sawtooth wave generator. Sawtooth waves are characterized by a linear ramp followed by a rapid fall. This waveform is crucial for creating a horizontal sweep on an oscilloscope screen, allowing us to visualize voltage changes over time. Sampling gates are electronic switches that allow a signal to pass through for a specific duration. They're commonly used in digital signal processing and communication systems. Unidirectional sampling gates allow signal flow in only one direction, while bidirectional gates permit signal flow in both directions. One challenge with sampling gates is the presence of pedestal, an unwanted DC offset in the output signal. Various techniques, such as using a clamping circuit or a pedestal reduction circuit, can minimize or eliminate the pedestal, ensuring accurate signal sampling.